on intermolecular forces. In this lesson, we're going to be talking about how molecular substances have different boiling points and melting points based on their structure and the intermolecular forces which are present between them. This is the bonding between atoms compared to the bonding within atoms or molecules. So we've talked about the three types of intramolecular bonding. This describes bonding between within atoms, such as metallic, ionic, or covalent bonds. But we're going to be discussing today more of intermolecular bonding, or which is bonding between different atoms or the same atom. So the intramolecular forces are quite strong, and as mentioned, they exist of three types: covalent, metallic, and ionic, whereas intermolecular forces are weak and they are attraction between molecules. It's key to note here that intermolecular forces, they attract between molecules and they exploit or are based upon polar and nonpolar substances. They're also significantly weaker in their strength to break those bonds. So if we look at the three intramolecular forces, we've got ionic there, covalent and metallic. And we look at the energy in kilojoules per mole to break those bonds, they're quite high. In comparison to the intermolecular forces, such as hydrogen bonding, such as dipole-dipole, and dispersion forces. You can see that the energy needed to break these bonds is far less compared to the energy needed to break those bonds, highlighting these here. The intermolecular forces are much weaker and up to 100 times weaker than intramolecular bonding. However, they do have implications for the molecules and the structure of atoms. So for example, the reason that this bug can float on water over here is because the water molecules have intermolecular forces, which creates a surface tension or creates a layer on top of the water that enables the insect to float. So they are relevant and important. The first of the intermolecular forces that we're going to describe today are dipole-dipole forces. This occurs when you have two dipoles, so a positive and a negative charge in a molecule, and it's specifically a polar molecule. The attraction happens between positive and negative ends, and that is given the delta positive and delta negative charges. So for example, we may have a hydrogen chloride atom and another hydrogen chloride atom here. This hydrogen atom is going to have a delta positive charge because the electrons are not going to be as dense over the hydrogen atom as they are on the chlorine atom. So if we have these atoms together, and then we have here a hydrogen chloride, you can see that there is going to be a delta negative charge on the chlorine atom and a delta positive on the hydrogen, and this creates an attraction between those two molecules, or an instantaneous attraction. This is known as dipole-dipole forces. So what does this mean? Why is this important? Well, the implications for such is, if we look at methanol is a polar molecule, as you can see here, and if you look at another molecule, which is of a similar structure, ethane, it is a non-polar molecule. The implication of this the dipole-dipole attraction, is that the boiling point over here is significantly higher. There's a higher boiling point in methanol than there is in ethane because of the intermolecular forces bonding between the atoms due to dipole-dipole forces, meaning creates more energy required to break these molecules apart from the liquid state into the gas state. So it has a significant implication in terms of boiling point and melting point, as well as other features. If you look at the second type of intermolecular force, it's known as hydrogen bonding. This specifically happens in polar molecules, so again, positive and negative charge, dipole-dipole attraction, and it happens between hydrogen atoms and which are covalently bonded to a specific set of molecules or atoms, known as nitrogen, oxygen, or fluorine. So these atoms here are obviously highly electronegative. They want to gain electrons very strongly with respect to hydrogen. So if you look at the electron density around these atoms, say for example a hydrogen fluorine atom, we're going to have a delta negative of the fluorine and a delta positive as a hydrogen. Because the electronegativity is far greater for fluorine than it is hydrogen, the electrons are going to be located more of the time over here. The hydrogen bond, or the hydrogen intermolecular force, is much stronger. It is the strongest type of intermolecular force. So if you look at actually what's happening in a hydrogen bond, we have a nitrogen atom bonded to three hydrogen atoms. That's an ammonia molecule, and this hydrogen atom is given a delta positive charge, given that because of the hydrogen atom has less electrons located in its vicinity compared to nitrogen atom. So it's negative with respect to hydrogen. The hydrogen atom will then form a bond to another nitrogen atom, or it may even be a hydrogen atom forming a bond to an oxygen atom or a fluorine atom. So this is a hydrogen bond. It occurs between a hydrogen atom that's covalently linked to an oxygen, a nitrogen, or a fluorine atom. The implications for this. So hydrogen bonding significantly increases the boiling point and melting point of the structure. If you look at the boiling point and melting point of atoms that have hydrogen bonding, it's much higher. Another implication of this is how the structures are arranged. So for example, take hydrogen bonding, which happens in water. Water is a molecule that's all around us. This molecule will have hydrogen bonding in a liquid state, where you have free flowing and movement of particles, giving it a liquid state, as I already mentioned. However, have you ever noticed that ice is the solid form of the substance of water, yet it floats? How many other substances do you know where the solid substance, so solid aluminium or solid steel, floats on molten or liquid steel or liquid aluminium? It doesn't happen very often. And the reason is it's usually hydrogen bonding. The way that the hydrogen bonds organize in the ice molecule or the solid molecule is in a cyclical ring or a sort of hexagon shape. This means that this substance is less dense because you have less particles per unit area compared to the liquid state, which is more dense. Obviously, you have more particles per unit area. So the implication for this is that ice actually floats on water because it's less dense due to the way that the hydrogen bonding aligns in the solid state. This here is an animation showing the difference between the intramolecular bonding, covalent bonds between the hydrogen and the oxygen atoms, and the intermolecular bonds occurring between them. As I mentioned, implications of hydrogen bonding is that it greatly increases the boiling point and melting point of a compound. We take ethane, we've got non-polar, so only dispersion forces, which we'll come to in a moment. We have methanol, which is polar substance, so we have dipole-dipole interactions, and then we have methanol, which has a polar molecule again, has both hydrogen bonding and dipole-dipole interactions. So the melting point and boiling point is significantly higher. Over 100 degrees Celsius increase in the melting point of methanol compared to ethane. The final intermolecular force we're going to discuss today is called a dispersion force. So dispersion forces happen between non-polar substances, and these are such as solids or liquids. So what happens is we have a temporary dipole. It's induced or happens with the random movement of electrons. So if you take a look at this animation or slide here, start with an unpolarized molecule. So we may have a hydrogen atom bonded to another hydrogen atom, or a fluorine atom bonded to another fluorine atom. At one stage, when they come together, we may create an instantaneous dipole. So the fluorine atom over on this side becomes slightly negative, delta negative, with respect to this fluorine atom. Initially there was no dipole, it was non-polar. Then we've created an instantaneous dipole. More of the electrons are located over here than they are over here, which will create a bond between the two substances. Again, it's instantaneous, it only happens very quickly and momentarily. That is our dispersion forces, how they're formed. So dispersion forces, although they only happen very quickly and very briefly, they actually increase the melting point and boiling point of that molecule quite a large amount. Not as much as hydrogen bonding or dipole-dipole attraction, but still noticeable. Also key to note is that the strength of the dispersion forces increases as the molecule increase. Given that if you have more electrons as the molecules get larger, so we're getting larger number of electrons here as we get down this table, which means we're having more dispersion forces, which means the boiling point is going to also increase as we move down to the higher electron dense atoms. Another thing to note here is that the larger molecules have higher dispersion forces, but they also have higher surface area, which means you can have more dispersion forces. So this molecule here, butane, 4 carbons, and then methylpropane, also 4 carbons. This one here has a higher surface area compared to this one, therefore has a higher melting point, as well as having more dispersion forces. The summary of today's lesson: intermolecular forces are found in substances, and they are either polar or non-polar. There are 3 types of intermolecular forces, as I've already discussed: hydrogen bonding, the strongest, dipole-dipole the next, and dispersion the weakest. What you should be able to do by the end of this lesson is distinguish and identify polar and nonpolar molecules from the previous lesson, explain why they're polar and nonpolar and how this has implications for intermolecular forces, identify the three intermolecular forces between molecules, rank their strength, and the implications for different substances. These are the questions that we need to complete 1 to 6 of chapter review 7.3 on page 174.